All right, hello, folks, and welcome to a very special interview with a lead meteorologist for the weather company. This is Ben Papandrea. He reached out to me when I put together my little video on Hurricane Melissa yesterday and was agreed to come on. And he knows a lot more than I do about hurricanes and weather forecasting and how all this works. So I thought it would be a great opportunity to bring him in, talk a little bit about this historic storm that's going on in the Caribbean right now, and learn a little bit more about hurricanes. So thanks again for joining us, Ben.
Yeah, thanks for having me. Super excited to be here.
Yeah, so maybe just walk us through kind of the latest with Hurricane Melissa. I know people are seeing it in their news feeds. They know it's a large storm. They know it's in the Caribbean and kind of bearing down on Jamaica as we speak.
Yeah, it's an absolutely incredible storm. The Weather Center is behind me, and we're just kind of a flurry of watching this data come in and just in awe at actually just how powerful the storm is. Right now, the maximum winds are 185 miles per hour. So that makes this the second strongest storm ever, second strongest hurricane. Okay, so there's typhoons,
Wow.
right? They're the same. Yeah, 185. Only Hurricane Allen, and Allen was in 1980, that had 190-mile-per-hour winds. So this is getting close to the strongest ever in the Atlantic. So absolutely incredible. The pressure is down to 892 millibars. So that would be the third lowest pressure. So just to give you an idea,
Yeah.
pressure decreases with height. You need to usually go up 4,000 or 5,000 feet for the pressure to be that low. So you almost think of it as like, the lower atmosphere has kind of bent down
Like
towards
an
the
inverted
surface.
mountain. Yeah.
Absolutely incredible pressure. So just to give you an idea of how strong these winds are, this is the equivalent of an EF4 tornado. So imagine that the winds are of that intensity. Now, of course, when we say those maximum sustained winds, they occur in a pretty small area, within the storm. But the winds, even just around that, is still, of course, incredibly intense. I mean, 180, even, normal category 5 strength, 150 and greater is unbelievable, never mind 185.
Right. That's just
So,
incredible. Well, what
yeah.
could you maybe talk a little bit about what were the conditions that allowed this storm to reach such strength? What sort of things came aligned together so that this storm could be such a monster?
Yeah, I could share my screen, show you a few things.
Yeah, that would be great if you want to
Yeah,
share.
let me do that.
Okay, you should be good to go.
Okay. Let's see.
Yeah, because I mean, visually, I think it's important to kind of see just how big this is, and talking through it's one thing, but yeah, the visuals and the satellite imagery is really good.
Yeah, yeah, absolutely. Hang on here one
Oh,
second.
you're good.
It's giving me the security thing.
Right.
And we'll be
Get through all the checks.
and then we'll be good to go. It's not letting me share the screen.
Oh, is that as on Zoom?
Yeah, it might be. Oh, hang on a second.
There we go.
There we go. All right.
No, you're
Sorry for the
good.
little blip there. Okay.
Yeah.
All right. If you can see everything.
Yeah, that looks
So
good.
this is a satellite image. I'm gonna show you this in a moment, but let's talk about the conditions first. So you in the video that you made yesterday, you talked about wind shear. So I know, when you see images like this, your brain just,
Looks like spaghetti, yeah.
explodes, right? You see lines everywhere and you're like, oh, what's going on here? So let's get the bearings on here. So here's Cuba
Yep.
right here, if you could see my mouse.
Yeah, I
All
can see
right.
the outline of the Florida and the Caribbean there.
You can
Yep.
see the outline of Florida. Okay. So and Jamaica, of course, being tucked up
Yeah, it's
in there,
obscured
kind
by
of
the
hidden by the
clouds.
clouds.
Yeah.
So this shows wind shear. So think of the red lines as too much wind shear, and then these green and yellow as low wind shear.
Right.
So wind shear is a change in wind speed and direction with height. So think of it as like, if you have light winds down low, high winds up above, that's shear, right?
Right.
And you can have different directions too. So hurricanes, they really will not come together if you have high wind shear. And if you look, Melissa was just in this perfect area of very low wind shear. So perfect environment, low shear environment. And then the sea surface. So this is sea surface temperatures. Now you often hear you need about 80 degrees, 26 Celsius. And if you look at the ocean, the whole thing looks warm, right?
Right.
And it's hard to tell for this. Really, the more modern way that we look for like the fuel for hurricanes is called tropical cyclone heat potential, or at this graphic shown here is ocean heat content. So what this does is it shows how far down does that warm water extend,
Hmm.
right? So hurricanes, they're blowing the water away, right?
Yeah, they're
And what
pushing the
happens when
water. Yeah.
yeah, they're blowing the water kind of away, cool water will come up from below, and the hurricane can almost kind of kill itself if that warm water is very shallow. What this is showing is how deep that warm water extends. And if you look over here in the Caribbean,
Yeah.
very deep extent of that warm water.
How do they
Here's
get that
another way to,
data? Sorry to
what was
interrupt.
that?
How do they get that data? How do they know?
So part of it is buoys
Okay.
that are in there that have instruments that extend down, and also satellite, so like altimetry, so they're able to like kind of peer through
See
the
through
water.
it.
So there's something called like a sea surface height anomaly, where they could see if the sea surface height is a little higher or a little lower than normal, and they can kind of estimate temperatures based on that. So they kind of combine it all together.
Okay.
And this is really helpful. So this shows kind of the depth, like how deep does
Okay.
that
Yeah, that
80
was my
degree
next
water
question.
go?
Yeah. So it goes, yeah, hundreds of meters.
Hundreds of meters. So if you think about Melissa, it was moving very slowly in this environment that had low shear and had all this sort of deep warm water. And again, I'm not talking about deep as far as how deep the ocean is. I'm talking about the extent of how deep this 26 degree Celsius, 80 degree Fahrenheit water goes. Plenty warm.
Yeah.
So
Favorable. Yeah.
yeah, it's very, very favorable. So this is just perfect conditions for it. An incredible storm. Let me show you. I discussed these specifics. This is an advisory from the National Hurricane Center that just came out. They're flying the aircraft recon around, and they just came out with that. That 185 mile per hour winds, like I told you. So this is 1 minute satellite imagery. So usually when you look at a website, the satellite imagery is every 5 minutes.
Mm-hmm.
So this is what's called a floater image, where they
Mm.
take scans every minute, and you could see the eye wall just starting to come on shore there in Jamaica, right in the western side of the island. So
Wow.
this is an infrared satellite image. Basically, you're actually looking at temperature, not clouds, right? So you're looking at the temperature of the cloud tops. And when we see very cold cloud tops like this in this circular pattern, it really means the hurricane is intense. So this is called the central dense overcast, the CDO. When we see this sort of circular,
Right.
very deep convection like that in this very tight. So usually sometimes you may think, oh, if the eye is big, maybe the storm is stronger. Actually, no. The smaller the eye is, little pinhole eye is a sign of a very intense hurricane, and that's what we have right here.
Okay, so to make sure I'm clear on this and other folks too, so the hurricane is like a cylinder. It has a vertical dimension.
Yes.
It's drawing in this warm water and air at the surface, kind of like a vacuum.
Hmm.
Then that's rising, and as that air rises, it cools. And now we're looking at, and then from the satellite image, we're looking at the top where it actually flows kind of out, right? It's almost shaped like
Exactly.
a spool for thread.
Exactly. You can kind
Okay,
of see that kind of outflow from the storm,
right.
right? The winds at the surface are circulating counterclockwise, right? Because it's an area of low pressure.
Yep,
And in the upper atmosphere, they're actually kind of fanning out, venting the storm.
right.
So you have to have a balance between that air kind of venting out at the top and the air coming in at the surface.
So right now, you'd say it's a very efficient, tight wound, compact system. Like it's not just that's a well organized, it's symmetrical, the very tight eye. I mean, this is kind of as textbook as it gets, isn't it?
Exactly, exactly. And I'm a little surprised right now that we're not. Oftentimes, when it starts that kind of poleward, and we say poleward, we mean like in this case towards the north. Usually, the storm will start to lose that circular shape. It will probably later today or tonight, and you'll see it becoming a little bit more elongated,
Right.
almost like showing you where it's going, and that's because of the wind flow. But let me show you something else that's actually really interesting. So this is a visible satellite image. Again, 1 minute. Visible means it's almost like taking a picture from space.
Mm-hmm.
Okay, so instead of looking at temperature, we're actually looking at what this looks like from space. Those plus signs, they're lightning strikes,
Wow.
live lightning strikes derived from the satellite. This is rare to see that much lightning around the eye wall at landfall. And it is a sign that the hurricane is likely still intensifying a little bit.
Right. Like the energy levels just off the charts. What are the oranges just other pluses in there? Is that what that those are just
Yeah, so
different
all the
colors?
pluses of the
Okay.
current lightning, it's just showing the age of the lightning.
Okay, I gotcha. Right.
So I think blue is like older lightning strikes. I'd have to look at the time frame is right down here in the lower left
Is
of
it
the lightning strike.
common to get that many lightning strikes such that it basically is defining the eye? Like even if we had nothing else on this image, if it was just plus signs, I could still clearly delineate the eye's geometry and size just off the lightning strikes.
Exactly, exactly. It's quite remarkable. Normally, there's not a lot of lightning in hurricanes. A lot of folks don't realize that. Like to get sciencey here for a minute, you really need to separate electrical charges by having ice in the clouds, right? So
Mm-hmm.
normally we have like water and ice crystals and all these things in the clouds. And ice crystals, think of them as kind of like fluffier, lighter. They usually get a positive charge and they kind of go up towards the top of the clouds, and the negative charges sink to the bottom, and you get that difference, right? That's creating the lightning strikes. The environment in a hurricane is usually kind of so warm that you can't separate the charges because there's not a lot of ice in the clouds.
Right.
But when you have really intense upward motion in the hurricane, you will get those sort of different precipitation particles that can cause lightning. So when we see this, we know the hurricane is unbelievably strong to have that ring of lightning around the eye wall like that.
That's incredible. And are those are not probably lightning strikes hitting the ground. Those are intra-cloud lightning. Those are lightning
They
strikes
they
within the
may
storm.
they may be both.
Okay. Hard to
They may
tell.
be
Okay.
both. Yeah, I think I'd have to look. So there is a network of lightning sensors on the Earth's surface, and then this is satellite derived lightning. Can't recall off the top of my head if the satellite derived is getting the ground strikes or both.
Right.
I'd have to check that. It actually doesn't matter in this
Yeah.
case. Just having lightning there in the core of the storm is pretty incredible.
So have you ever seen with other hurricanes you've watched over your career? Have you seen that number of lightning strikes around the eye like we're seeing right now?
Um, I'd say I think I remember perhaps a few storms,
But it's
but
pretty
this
rare.
is
Yeah.
this is for the record books to be coming on board, like making landfall with that much lightning is pretty rare. It's going
Wow.
to be a hopefully anyone that's in the path of this is in a shelter because it's a horrible situation.
Yeah.
It really is. It would be I would be scared to death. If I was right there.
Well, I think that's the thing we don't comprehend well as humans unless you've been through one is that, like a windy day here in southern Idaho is like 50, 60 mile an hour winds and you're like, "Holy cow, it's cruising." But this is three
Yeah.
times that, and you're adding in the rain and lightning perhaps, and if you're in a coastal setting, the storm surge, like it's just this cacophony of like hazards, landslides if it's in
Yes.
topography, just a crazy system. So it's hard really to
Yep. Yep.
comprehend what's going on.
Yeah, it really is. And the storm is moving, I think right now it's like 7 miles per hour. But if you think about it, it was moving as low as 2 to 3. So there's sometimes I hate to tell people this. It almost sounds a little too unscientific. There's a very old rule of thumb that if you get the motion of the hurricane, the speed, and you divide it into 100, you get an approximation of the rainfall. So
Interesting.
do 5 into 100, you're getting about 20 inches of rain,
Hmm.
right?
Interesting. Yeah, I hadn't heard that.
Yeah. It's a
Well, it makes sense though because
um
the slower it's going, the more that
yes.
it's stalling over a given location, so you're getting higher rainfall amounts. That makes sense.
Yes. Yep. And you have the Blue Mountains, which are in this part of Jamaica, which I think they run 7,000 feet or so. So you get that orographic effect, and the flow is coming up like this right into the mountains, and that area gets lifted, and you're enhancing the rainfall too. I'm sure the heaviest rain will be in this area. Um, Quite likely there are places that will exceed 2 feet of rain, along with an incredible storm surge.
Yeah.
Incredible to say. I don't know how many more ways I could say it.
Right. And then what do you think its effects will be? Obviously, it's Jamaica's like right in the line of fire there, but as it moves over Jamaica back over the water, does it look like it'll probably still be a major hurricane, but what do you think its effects will be as it heads like to the north over eastern Cuba?
Yeah, so I think once it gets across Cuba, it might still be a major hurricane, but it'll start moving along at that point. It will certainly create a lot of damage. There'll probably be a storm surge over here in this south coast part of southeastern Cuba. Certainly wind damage. Definitely at a level quite a bit less than what they get in Jamaica, but I don't want to diminish it and act like it's not a big deal. It certainly is.
Right.
But not to this really incredible event that we're having over Jamaica. And once it gets beyond Cuba, we expect wind shear to increase, start to weaken. It probably will not be a major hurricane once it moves across the Turks and Caicos Islands. And I could show you. So this is called water vapor satellite imagery. So it's kind of like infrared, but we're
Mm-hmm.
able to see water gas. So think moisture. Okay.
Right.
So we're looking at moisture in the atmosphere, and we're also looking at clouds. So this kind of yellow, orange, that's dry air, right? And then these are obviously clouds. There's the hurricane. And if we take out my little pen, see the way this flow here?
Yeah.
So there's high pressure out here, and that kind of exerts a force this way. So that's why the hurricane is moving in that direction.
Right. It's steered by the circulation around those high and low pressure areas.
Exactly. And I'll get even a little bit more sciencey on you here and,
No, we
and show
love
you
it. This is
something.
good.
Yeah. So this chart, again, let's get our bearings. So here's the US, right? There's the hurricane down here. So we're looking at the middle part of the atmosphere. All right. So think
Like we're
almost the level of where you fly a
Yeah, I
plane.
was gonna say exactly. Yeah, like at 30,000
Okay.
feet or something. Yeah.
Yeah. All right. So think of these lines as pressure lines. They're kind of like pressure lines. And the wind is flowing along those lines. So here's the hurricane. So see that wave there? All right.
Mm-hmm.
So let me grab the pen here again. So there's that high pressure, right? Here's the hurricane, right? Here's that here's that wave there that's pulling the hurricane in that direction. All right, so keep that in mind for a second. Now I'm going to put it in motion. Keep your eye out over here, kind of towards the land of where you live, right?
Yeah.
You're a little off the map.
It's all right. We're used to
Now,
that.
yeah, watch what happens. Okay, keep an eye on this.
Mm-hmm.
Watch the hurricane as it goes to the north. So this is what we call an amplifying trough, right? Think of it as a
Mm-hmm.
wave, like a
Right.
like a wave, right? And think of the wave as getting bigger with time.
Right. So stronger
That
low pressure
will
center there. Yeah.
exactly. Eventually, that wave captures Melissa, see that, and then rockets it off towards the northeast. So right about this time frame, it's just about passing Bermuda. So this just goes to show you sort of like the dynamics in the atmosphere of
Yeah.
how these things play a role. Now, last week, just to give you an idea of the complexity of forecasting, there was data that the timing of this trough was such that it was forecasting Melissa to actually rocket towards the US.
Really? Wow.
Yeah, so we didn't tell anybody that because we thought it was unlikely,
Yeah, and it was so far
but
ahead time-wise.
yeah,
Yeah.
but it got us nervous that, this is a lot of this sometimes it's like a timing game,
Yeah.
with these things, moving around.
Well, and the
So,
further out you are with the models time-wise, then, like you said, the less certainty you have. Like right now, it's hitting Jamaica, it's hitting Cuba, it's moving to the northeast, but you couldn't tell me like where this thing's going to end up in a week with any certainty.
yeah. Yeah, it's you know
It's probability, yeah.
exactly. And I could show you here. I'll pull up there's this new I can show you all kinds of data here, but
No, I love all these weather sites. They're great.
yeah, this is one computer model actually that Google has now. It's called the Google DeepMind. Let me click on this. Hang on here.
So that's looks like different forecast tracks for the hurricane.
Exactly, they're different forecast tracks. Now, if I put this on, right? So this is remember remember the very first Jurassic Park, you had Ian Malcolm talking about chaos and the
Chaos theory,
butterfly
right? Yeah.
effect. Yeah,
Yeah.
remember that one? He did that little. A lot of people don't know that chaos theory started in meteorology.
Hmm.
It actually 1960s. Edward Lorenz, he was an MIT scientist, and he was starting out the very first computer models, like really rudimentary, like weather models at that time. And he was putting data into that model, and he ran the model to see the outcome. And when he made the data a little bit different, the outcome
Drastic. Yeah.
way different,
Yeah.
way different. And he was like, mind blown, what's going on here? And so he essentially came up with this thing called chaos theory, and it's like a very foundational thing in meteorology. And what we do now, and what we've done for a while, is we put the data into the computer model, and we call that the operational model. So it's I could spend an hour on this, but let's
Right.
just say
Yeah.
we take an observation of the planet, we put it in that model, we run it, we call it operational, okay? Then we do what's called perturb it, make it a little bit different, and then run the model again. And then change it again and run it again.
So are
And then
you
we
just
call it
change
an
sorry, are you just changing like little variables? Like, well, because the operational model would be what the weather is at that specific time. That's hard data. But
yes.
then you're trying to look forward. That's the whole point of the forecasting. And so you're just making small tweaks to the variables to see what the possible outcomes would be. Is that pretty
It's
accurate?
it's not necessarily the physics and the dynamics. It's kind of, so think of it like, so we don't necessarily put the raw data into the models. Think of it as we have the earth and everything is represented by the models. It, is it the land dry? Are there trees? Are there mountains?
Right.
Everything, water, all of it, right, is in there. And then it's like we update the earth with new data and we kind of blend it with the old data. Because if you just sort of wipe the slate clean and put it, it introduces errors,
Yeah.
right?
It has to know how
So
the system works. It has to. So it's almost like machine learning, isn't it? Like just sort of like it's
in a
it's
sense,
looking for patterns and what's happened in the past and what's likely to occur.
yeah, it's
Okay.
so there's part of that is too that's called like persistence and climatology, where some of that's built into the model, in a sense where we're making sure the model remains stable by um, refreshing the data, not wiping it completely clean, right? And then think of, I'll make a really easy example. Let's say we take an observation and we say it's 50 degrees, right? 10 Celsius. What if it's actually 9.8 Celsius and not 10? Or what if it's 10.1? So That's what we do. We vary the data a tiny bit by the possibility of there being some little errors in there. And then we get this, they're called ensembles, kind of a range of outcomes.
Mm-hmm.
And usually we blend those ensembles together to help us make a forecast. So we call it the ensemble mean. So a lot of modern meteorology is done this way, where it's not just one computer. It might be the same computer model, but that model might be run with 100 different little variations in the data.
Right.
Right.
Right. Then you get a higher, and then the output, the outcome is a higher probability model or sort of template, I guess, of like what is likely to occur.
Absolutely. Exactly.
Yeah.
Exactly. And oftentimes, when the Hurricane Center makes its forecast, they will blend many models together. And then, of course, use their experience and knowledge and say, well, the blend shows central Jamaica, but in our experience, this, that, and the other thing, maybe they'll be a little to the west. So, obviously we're not just, what we joke about in meteorology is like what we call rip and read, where you just take the data and you just, and I'm sure that's the same thing, and it's the same thing in geology, right? Like you want to make sure you interpret the data correctly.
Right. And then a couple hours go by, you have new data, right? There's the system is, the hurricane is moved, there's new pressure data, maybe a hurricane hunter data, whatever. So that goes into another model that gives you another blend, and then you can just keep updating these as you go, I guess.
Exactly.
Wow, very cool.
Exactly. It's kind of like a living system,
right?
That's being constantly updated.
Right. No, that's fantastic. So I can see all the different squiggly lines. So imagine, can you zoom out and see where all those lines go to the north? Does it? Imagine they get further afield, as you go further north, because it's like the certainty's not as good. It's like, well, it could go a lot of places.
Yep. Yeah. Oftentimes we call this the spaghetti plot, because it looks like someone just kind of threw a bunch of spaghetti on there.
Yeah, a bunch of noodles.
With all these lines that are there. But this is kind of like what we live with every day in forecasting. It's just kind of not something that we discuss because we don't want to confuse the heck out of people.
Right. I mean, that's the hard part, is that it's a forecast. It's not a prediction. And those are two, I teach my students, those are two very different things. A prediction is very specific, time, place, magnitude. But a forecast is probability. There's an 80% chance of rain tomorrow between 2 and 4, or, whatever. And people don't like to deal with that kind of uncertainty in their day-to-day lives, but that's the nature of the beast.
Oh yeah, and we struggle with sometimes with the communication of forecasts too, because if you tell somebody 30% chance of showers, right? And there's no showers. So I thought you said it was going to rain.
Right.
No, we didn't. We said it's a 30% chance, right?
Yeah. And really, doesn't that mean like there's a 30% chance that sometime during that time period, like it doesn't even tell you amount, like one drop of water falling out of the sky. Well, there you go. The water fell out of the sky.
Yeah,
so it doesn't even convey like amounts or.
So usually when what we talk about is measurable precipitation. So if you get 100th of an inch, right, 0.01, that's usually what we're tying the probability to, is that you could actually measure the precipitation to some extent, not just kind of a sprinkle that doesn't add up to anything. But we're moving more and more towards, trying to be as clear as we possibly can about the forecast and communicating it. I mean, there's been some problems in the past, and even like the National Weather Service is sort of redoing the way that they communicate warnings and advisories. I think a lot of folks out there are confused by, winter weather advisory, winter storm watch, winter storm warning, and hurricane. Like, what does this all mean? Shouldn't we just say, weather alert maybe, or make it easier?
Yeah. I mean, it's a two-way street. Definitely the forecasters could maybe communicate more clearly, but the public also needs to like learn a little bit and understand the system.
Yes.
And not demand such certainty. So
yeah, absolutely. And another thing too is, as scientists, myself and you, sometimes we oftentimes don't realize that people may really not even understand what we're talking about. And even like the line here, and I had this is a while back. What does that line mean? And I'm like, that's the eye. That's the path of the eye. We're
Hmm.
forecasting the path of the eye. And I thought to myself, whoa, there may actually be quite a lot of people that don't realize what that line
Yeah.
means.
Or they may look at it and be like, oh, it looks like my town is not where the line is, so we're fine. We shouldn't even have to worry about this thing because it's not intersecting my town. When in fact, that's the eye, but the swath of impact is 300 miles wide, and you're going to have to deal with this thing. Just not deal with maybe the
It,
worst part of it.
exactly. And I'm going to contradict myself here a little bit, myself a little bit. Where the storm goes, that eye, it absolutely matters, right? The outcome of how much damage there is and who's hit the hardest or what location is hit the hardest. But we will tell people don't focus on where the line is for the forecast because it is a forecast and it could change. Let me give you a story. So if you're in a hurricane warning, you should be prepared for a hurricane, even if the line isn't near you.
Right.
2004, I remember being in the forecast center and Hurricane Charlie. The morning forecast was for Hurricane Charlie to track, if you could see my little hand,
Yep.
like this, and hit up here in like the Clearwater areas, like Pinellas County in Florida. So this is the morning forecast was calling for it to be up there. So everyone in the Tampa area thought that they were going to be getting full blast major hurricane. You know where it went? 100 miles to the south over here. And that changed only 6 hours before landfall.
Wow.
They were in a hurricane warning. So imagine you lived here. It went into like the Punta Gorda, Port Charlotte area, which is north of Fort Myers, so right here. So it was almost 100. So what happened is the eye was moving towards the northeast. Last minute, it just went like that. And since it's was approaching the coast at that sort of that angle, all it
Yeah.
takes is just this, and it ends up much further down the coast.
Yeah. No, it's a totally different community that thought they were kind of like out of the crosshairs. Now they've got to scramble and be prepared for getting the brunt of it.
Yep. And we, meteorologists forecast, we're doing this all around the world, right? So we've seen these things happen so many times, and we just, please, if you're in a hurricane warning, listen to it. Even if you see that line is like not right next to you,
Yeah.
at the last minute, something could shift, and then you're not prepared.
Yeah.
Uh,
No, good advice. Wow. Well,
yep.
anything else about Hurricane Melissa or that you want to share before we let you go for the day?
Again, I would say unbelievably strong storm. From a science perspective, it looks beautiful to us on satellite, and it's amazing. But it's a sobering situation
Right.
as this will be a catastrophic event
Yeah,
for
it's going to cause
for Jamaica.
fatalities. It's going to cause billions in damage to some of these countries, and yeah, just one reason why science is important and why we got to
Absolutely,
keep working at it.
absolutely, and we're getting better at this hurricane forecasting.
Right.
It's improving, year after year, with more and more people living near the coast. Right, the future is about mitigation.
Yep.
Right,
Yeah.
just like with earthquakes.
Yeah.
Right.
Right. Just being better prepared, having better structures in place, and preparedness for sure. So, well, this was awesome, Ben. You're an amazing communicator. Thanks for teaching us more about hurricanes this morning. I'd love to come back to you again if there's another, severe weather thing like this that happens sometime.
Absolutely.
It would be great to have you on again to kind of walk us through it. So, thanks so much for giving us some of your time today, and we'll hopefully catch you next time.
Yeah, thanks for having me. Really appreciate it. It was
Okay.
fun.
Thank you.
Yep.